We are now.
Okay, great. So yeah, let's go ahead and do another theoretical example. This is C right here. Assume that A is 4 by 4 and B is 4 by 4 with the determinant of A equal to -2 and the determinant of B equal to 3. What I want to do here is find the determinant of A inverse B transpose times 2B quantity inverse. So these are kind of theoretical problems where you essentially have to use properties of determinants to figure them out. So can you guys just help me real quick and remind me, how does the transpose affect the determinant? No effect. How does inverse affect the determinant? Does anybody remember that one? So the determinant of the inverse of a matrix? No. So if the determinant of A is 5, what's the determinant of A inverse?
5.
Over 5?
Say again?
1 over 5?
1 over 5. It's reciprocal. Right? It's reciprocal. You guys know that. So we're going to basically have to flip this over. And what about the determinant of a product? So if I have the determinant of a product of two matrices, how do I find that determinant? The determinant of each individual one, and then what do I do with each of the individual determinants? If it's determinant of A times, okay. If it's determinant of, let's use different letters here. Do we have a property for this? Determinant of X and then what?
Determinant of Y.
And determinant of Y, and then what do I do with the two numbers? Just multiply. Okay. I thought I heard somebody say add them. I was like, no. You multiply them. So it's just determinants respect multiplication. So multiplication, that's perfect. Okay, great. So let's start working on this then. We kind of got the idea here. So to do this determinant, I'm basically going to take the determinant of the first part, which is A inverse times B, transpose, and then multiply by the determinant of 2B inverse. Okay? So we have that. Now you guys already told me that the transpose does nothing, right? So I actually, what I can do here is I can just take off the transpose and then just do the determinant of A inverse by itself and the determinant of B by itself. Okay, so that's this first part. And then I'm going to divide. Remember, you just told me that the determinant of the inverse of the matrix is just the reciprocal, right? So I'm going to put the determinant of 2B on the bottom. So this is just rewriting, breaking it apart, basically, into little pieces. So the transpose is gone. The inverse has created this reciprocal on the bottom. And A inverse and B have been separated. Got all that done so far. Okay, so what will be, let's start putting in some numbers here. What will be the determinant of A inverse? You have to look back at what I gave you, right? The determinant of A was -2. So the determinant of A inverse is just 1 over that, right? -1/2. Okay, and what was the determinant of B? 3. Okay, good. And I have to divide by the determinant of 2B. What's the determinant of 2B? Be careful.
Oh.
Do you remember?
It's 9.
2 over 3.
9.
2 to the 4.
It's 3 squared. Or, oh, it's 4 by... Oh.
The size of the matrices is important. It's like you multiplied each row of the matrix by 2, right? I'm glad we're reviewing this. Okay, it's like we've multiplied each row of the matrix by 2. So you pick up 4 factors of 2 from whatever the original determinant of B was, which was 3, right?
Yes.
That's the answer. That's the answer. So it's 2 to the 4th times 3. The factor of 2 has to be powered up by whatever the number of rows of the matrix is, because each time you multiply a row by 2, the determinant goes up by a factor of 2. And here you have 4 rows where you're doing that. Agreed? Okay, perfect. So now the 3's cancel, and you end up with 5 factors of 2 on the bottom, so that's just 1 over 32. Oh, there's a minus. I lost my minus sign. Now are we okay? Okay, great. So that's the answer. So properties of determinants. Guys, there's a couple of great examples in the group work on properties of determinants. There's this kind of problem where I give you some initial determinants and ask you to find some of these other determinants. There's also the examples, and I would suggest you look at these as well. I wasn't going to do one right now, but there's also the examples where I say, suppose that the determinant of, A, B, C, D, E, F, G, H, I is equal to 5, right? And then I say something like, okay, so then tell me what would be the determinant of 3D, 3E, 3F, A, B, C, and G plus 2A, H plus 2B, I plus 2C, or something like that, right? These are also nice problems. Basically what you're doing here is you have to look at the matrix and say, what? Oops. Hello, everybody. Sorry for crashing on your party here. Get this thing. This is really a problem tonight. I've lost the focus on this thing. There it comes. Okay. Oh, man. Everybody's going to really wish they came to the review. Hope everybody's okay at home. There was no earthquake here. We're just having trouble with the tripod on my camera tonight. It broke right before the review, so we're having trouble keeping this thing propped up properly. But anyhow, this is a nice problem here. Basically, you have to take the matrix that you're starting with and look at what EROs happened to get you to this matrix. So for example, you can see that the first 2 rows got switched. So that brings in a minus sign. There's a factor of 3 that went through one of the rows, so that picks up a factor of -3. And then it looks like we added 2 times one row to another row. Well, that does nothing to the determinant, right? So I guess I am doing this example. So what would be the answer here? -15, exactly. So the reason being that you started off with a determinant of 5. You multiplied a row through by 3, then you switched 2 rows. That's a factor of 3, and -1 creates a -15 out of the whole thing. And the other ERO does nothing to the determinant. So it's asking you to remember the properties of determinants. Either one of these types of problems is kind of asking you to use properties of determinants to evaluate other determinants. Okay? Does that make some sense? Okay, great. Now that we've got the camera all set up, I'm going to move again, Nick. Oh, goodness. Okay, I've got one more theoretical problem here. Maybe I'll just go right here so Nick doesn't have to work so hard to get the camera working. Okay, so let's do part D real fast. Oh, this one people mess up a lot, so I really want to go over this. So if A is an 8 by 11 matrix with nullity of A equal to 3, then true or false? True or false? the row space of A is equal to R8. True or false? The row space of A is equal to R8. So, you know, it doesn't hurt to kind of visualize it a little bit. You have 8 rows here, right? 3, 4, 5, 6, 7, 8. It's an 8 by 11 matrix. And so that's the kind of the visual that you might have in mind. Now, based on what we have there, I mean, what kind of information can we take advantage of? I mean, what are you thinking about right now? Okay, there'll be 3 unpivoted columns because that's what the nullity is telling me, right? So remember, the nullity is the number of unpivoted columns in the matrix. While we're at it, is there another number that we might already know? The rank, right? So what would be the rank of this matrix? Right, the rank plus the nullity adds up to the total number of columns, which is 11. So the rank has to be 8 if the nullity is 3. So basically the idea here is that you have, I'm just going to kind of draw a little bit of a visual of this. You have 8 pivots. Remember, the rank is the number of pivots. And then you have 3 unpivoted columns at the far right, which would be thought of as corresponding to free variables if we were solving this thing out. Okay, so based on all that stuff we've done so far, is that, notice I haven't even tried to answer the question yet. I've just tried to put down the stuff that I know and give myself a visual. Now let's think about this question. So based on this, the question is the row space. Remember what that is. The row space is the span of the rows of the matrix. So each row forms a vector, right? You can think of it as a horizontal vector. So each one of those rows is a vector, and we're taking the span of those. So would it be equal to R8? Remind me again, how do we find the row space of a matrix? We take the matrix, we row reduce it, we find our pivots, and then we take those rows, don't we? We don't have to go back to the, remember, if you're doing column space, you have to take the row echelon form and go back to the original matrix to take the corresponding pivoted columns. But for row space, you don't have to do that. So our basis for our row space would just be these 8 rows. It makes you want to say that it's true, but it's not. It's not true. What is true is that the dimension of the row space is 8. Remember, I think you guys have a handout that I wrote out, like kind of by hand somewhere. Oh, he's got it right there. Right? If anybody needs that copy of that hand, that was like a recap that was too long to put on the board, so I just handed it out in class a couple months ago. That kind of tells you, okay, so row space, the dimension of it is just the rank, which is 8. So the row space is 8-dimensional. The dimension of the row space of A is 8. Okay, so but then why am I saying it's false that the row space is equal to R8 if I'm saying it's 8-dimensional? Why is it false? I'm telling you it's false.
There's 11 digits.
Because there's 11 slots. Exactly right. If you go looking at this row, right, that's not a vector in R8. That's a vector in a completely different universe, namely R11, right? So these vectors do not have anything to do with R8 at all. It's a little tricky because the dimension is right. The dimension is 8. But guys, there's lots of 8-dimensional vector spaces that are not R8. Right? So I mean, heck, the 4x2 matrices is 8-dimensional. P7 of R is 8-dimensional. There's lots of different vector spaces that are 8-dimensional. Just because the dimension is 8 doesn't mean it equals R8. It could be something else, right? Okay. So it's false for that reason. And what your justification would need to be, what I would want you to say is, I would simply want you to say that the row space of A is a subspace of R11. And if it's a subspace of R11, then it doesn't equal R8. It might be isomorphic to R8, in order to use a fancy word, but it's not equal to R8. It's not literally R8 at all. Okay. As a quick follow-up to that, let me just ask you this as a true-false. The column space of A is equal to R8. Would that be true? The column space of A equals to R8. That would be true because look at your columns. Your columns have 8 slots, right? And this is 8-dimensional, and it's a subspace of R8, so it does equal R8. If you have an 8-dimensional subspace of R8, well, yeah, that would be R8. It's the only thing it could be. Clear enough? So this one would be true. This one would be true. And what you could say here is just call space of A is a subspace of R8 and dimension equals 8. So call space A equals R8. Freddie, you might do a little better if you just relocate. I think Louise took off, so if you're having a hard time seeing my writing, just feel free to move. Okay, everybody all right on that? Okay. So we practiced some of these earlier, back in chapter 4. Just figured it would be good to look at another one there. Okay. All right, so I did that, did all of that. Let's see what else I haven't done. Doing pretty well here. Go ahead and do another problem. So those are kind of just some examples of theoretical type questions. To give you a few ideas on that. Okay, let's, we're getting close to 10. It is 10. I'm going to keep going, but I might ask you, do you want me to show you this, or kind of go somewhat quickly through some of the other ones, because you might tell me that, no, I've had enough. But I just want to make sure that you at least have an idea how to do these. It's not very much left on the sheet, actually. So problem number 10 is just another one of these differential equations. So we may not even need to do it if you guys tell me that you're happy with it. So y double prime plus 2y prime plus y equals e to the negative x over the square root of 4 minus x squared. Okay, let's take a look at this one. And what I'm looking for mostly here is what method or what topic or what's going on with this problem.
Variation of parameters.
Oh man, I got a good response out of that one. It's variation of parameters. Look, it's only second order. I don't know how to annihilate a fraction, right? I actually had one of these on the midterm that you took last week. So it's just a matter of writing down the auxiliary equation, right? And, you know, honestly, what I had the biggest problem with for people on the midterm was just things like taking the derivative, like doing the Wronskian. People were having trouble just, because basically what's going to happen here is you're just going to get a repeated root of -1. And so then when you do your Wronskian, your two basic solutions are just going to be e to the negative x and x e to the negative x. And I just had people who were having trouble with just the product rule on some of these. So, you know, they could have studied twice as long for the midterm. It wouldn't necessarily have made them not make that mistake. So you have to keep that in mind. Sometimes these things are not, it's not about the content, it's just about the mechanics of it. So I think, are people okay with this, that I don't need to solve this one out? People could do it? Trust me, this one, I set it up, there is a solution you can read later, but this integration that you end up having to do to find the U1 and U2 is in the table of integrals that you'll have. So, you know, I'm always going to be mindful of that to make sure that the integrals are pretty reasonable. Okay, so I won't go ahead and finish that one, which basically means I've only got, well, I've got a couple more on inner products here, and then I've got one problem on a linear transformation. Is it one-to-one onto both or neither, which we can either do or not do. Maybe let me just write it down and see what you think. Maybe you guys will tell me you don't need this one either. I've just done so many things already. Between what I've done already tonight and what we did just last week, I've done a lot of stuff. So here's, oh gosh.
It works better this way, I realized.
Okay, we're having camera difficulties again, but Nick is doing his best with it. Okay, while he's fiddling with that, let me just write this one down. This is number 5.
It's
T
stable.
goes from M2 of R to R2 via T of A, B, C, D equals A minus B minus 3C, comma, 2B plus D. Okay, so this problem actually has 3 parts here. The first of which maybe we should do because it's kind of newish, or not newish, but it's something we haven't done for a while. So show, part A, show T is linear. Show that T is linear. So would you guys know how to do that? Maybe we should write this out. Yeah, we have to show 2 parts, right? We haven't done this for a while. Let's just do it real quick. So T respects addition. We have to do T respects addition and T respects scalar multiplication. Those are the 2 parts of this. Okay. How do we show that T respects addition? Okay, so we can set up notation. We have a matrix A, B, C, D. And what else do we have to have? Another matrix. Yeah, maybe I'll use E, F, G, and H. Yeah, so we need 2 matrices. So let's just say I don't even need to name them with the capital A and capital B. I'm just going to say let A, B, C, D and E, F, G, H be elements of M2 of R. So you start off by grabbing 2 vectors that are in the vector space V. And you just simply write them down. Okay? In the same format as what your transformation says. Okay, and then what do I need to do next?
You need to show that A plus, or the transformation of A plus B.
Okay, the T respecting addition just means that T of, I'll just write down the formula here. T of the sum of the 2 vectors is just T of the first vector plus T of the second vector. So in this case, our vectors are these matrices. So I'm going to write down 2 matrices here, A, B, C, and D, plus E, F, G, H. I have to transform that, right? I have to transform, this is really V1 plus V2. V1 plus V2. Okay, so what do I do first here? Add the matrices. Okay, good. So I don't transform them yet. I just add the corresponding entries, right? So what's that going to give me? A plus E, B plus F, C plus G, and B plus H. Got it. Okay, so now we've created a single matrix here. Now we can transform it using the formula at the top. Okay, so what's the formula tell me? Well, A minus B minus 3C. Well, that just means I take upper left minus upper right minus 3 times lower left. So upper left, in our example now, is A plus E.